Hi guys. Today we're going to start going over the life cycle of the star, if it loads. There we go. Heads up, I am going to be going through this relatively quickly. There are lots of slides, so feel free to pause and take notes, and you'll need a lot of this information for your flow chart that you're going to have to do. So star formation is ongoing. Star forming regions called nebulas are all over our galaxy and others. So this is just one little nebula here. When you blow it up, it looks like this. So star formation happens when a part of a dust cloud begins to contract under its own gravitational force. That dust cloud we would call a nebula. As it collapses, the center becomes hotter and hotter until nuclear fusion begins in the core. That's kind of the first several steps of the flow chart. So don't necessarily worry about writing all that down. I'm just writing myself a note here. So when looking at just a few atoms, the gravitational force isn't strong enough to overcome their motion, the energy of their motion. So you need to have enough of them close enough together to actually start to get things to gravitationally pull together. So at stage one, don't necessarily worry about the stages in this, because this book likes to break things down into a ton of stages. So you start off with a nebula, and the nebula starts to contract and fragment. So you see the one nebula here breaks down into smaller pieces, and those smaller pieces kind of coalesce together. And then it would end, this one nebula would end up being, this is like 16 stars over here. The main point here is that one nebula does not make one star. One nebula makes lots of stars. So individual cloud fragments begin to collapse. Once their density is high enough, there is no further fragmentation. The interior starts to get hot, and it's about 10,000 degrees Kelvin. The next step, so on your flowchart, I would go nebula and then protostar. The next step is the protostar. So the core of the cloud is now a protostar. It makes the first appearance on the HR diagram. It's up here in the top right. It is in the top right because it is very large. So notice this is formation of stars like the sun. Notice this is 100 solar radii here. This is one solar radius. So notice the sun is sitting right on this line. So the protostar that formed the sun was 100 times the size. But the temperature is relatively low. But the luminosity is high. So that's how it earns that place on the HR diagram. So planetary formation has begun, but the protostar is still not in equilibrium. All heating comes from gravitational collapse. Going from protostar down to main sequence star, which is what's going to happen here. You see it kind of gets smaller and smaller and smaller, starts heating up, getting a little hotter, moves over towards the yellow part of the HR diagram here. Luminosity goes down because the size goes down, even though it's getting hotter. The core reaches about 10 million degrees Kelvin, and nuclear fusion starts. The protostar has now become a star. The star continues to contract and increase in temperature until it's in equilibrium. That's when we call it a main sequence star. So that's kind of the adult version of the star, and it will remain there as long as it has hydrogen to fuse. If you have a larger chunk of stuff, it will kind of do this. So this middle one is what made the sun. If you have a larger chunk of the nebula, it would end up just further up the main sequence here. If you have a smaller chunk, it would end up further down the main sequence down here. Main sequence is a band rather than a line because the stars of the same mass can have different compositions. So they can be made of different stuff. Most important, stars do not move along the main sequence. Once they reach it, they're in equilibrium and do not move until their fuel begins to run out. Their fuel is hydrogen, right? So they're going to squeeze hydrogen to make helium. And as long as they can do that, they'll be on the main sequence. But once they run out of hydrogen, then they can't stay on the main sequence anymore. Some fragments are too small for fusion to ever begin. So on your flowchart, off of a protostar, I would have like another little curly thing off to the side showing a brown dwarf. Okay, so brown dwarfs are basically failed stars, and they just don't have enough mass for fusion to start. So This is just some pictures. So here is Orion, right? Here's the Orion constellation. In this one tiny little region down here is the Orion Nebula. And in this one tiny little region of the Orion Nebula, you have this big cloud. And within that, they've kind of blown up two different parts. This has a bunch of, both of these actually have a bunch of stars. This has 1, 2, 3, 4, I'd say 5, 6 or 7 stars here. And there are like 4 or 5 in this as well. This is showing what a protostar looks like. This blackness is because this is what we call the accretion disk, or a protoplanetary disk. This will end up becoming all the planets, asteroid belt, all that stuff out there. Here, it's a little bit further along, so you start to see the light poking out behind the cloud of debris. This is just an artist rendition of basically the same thing. It's very cloudy to begin with. Now the planets have started to kind of win their gravitational tug of war a little bit. And then once the solar winds start, that will kick out a lot of the dust. These are jets that are coming out of a protostar as it's starting to form a star. This is just an artist rendition of the same thing. Star clusters can be super helpful to astronomers when they look at this, because in a star cluster like this, all these stars were basically born at the same time. So then we can start to look at how much mass they have to tell us how long those stars will stay in each part of the life cycle. So here is the Pleiades, which is a star cluster. And notice all of them are like basically right here in the main sequence. I'm going to pause there, and then we'll pick this up on the next one.